Okay. So let's talk about hardness, and actually we'll talk about hardness and alkalinity. So hardness is a term that's often used to describe the ability of a water to cause soap scum, to increase the amount of soap that's needed, to cause scaling on pipes, to cause valves to stick, or to leave stains on plumbing fixtures. So those of you that have lived on campus have experienced water that is what we call extremely hard. Typically that hardness is predominantly due, all right, I'm not cutting this area, predominantly due to calcium and magnesium. On the MSU campus, there is a significant amount of iron in the water. Now, in most groundwaters, iron would be present as Fe2+, but then in the presence of oxygen, it gets converted to Fe3+, and that's that orange color that you see in the water at MSU, or you have seen. And then manganese is typically Mn2+ in the groundwater, so it's typically in a reduced state, and it's oxidized to Mn4+, and its complexes are typically a blackish color. So you can see in this pipe, this scale that's formed here. This is predominantly calcium carbonate that coats the inside of the pipe, increases the roughness of the pipe, which increases head loss, and it also decreases the internal diameter, which decreases the pumping capacity. So we worry about it for that reason. Basically, hardness is formed from the dissolution of limestone. So we have calcium carbonate or calcium magnesium carbonate minerals in the groundwater. They can dissolve over time, releasing calcium and magnesium and contributing to hardness. We describe the hardness of water on a scale from extremely soft to very hard. So for those of you living in East Lansing or Lansing, typically the water will be somewhere around 100. And that's milligrams per liter as calcium carbonate. Extremely soft water, 0 to about 50. On the MSU campus, the hardness is typically around between 300 and 400 milligrams per liter. The new treatment plant will not remove hardness. It's designed only for iron and manganese removal, not for hardness removal. And you can see here from this map that the hardness levels vary significantly. These are actually in grains per gallon, and I give you the conversion later. But you can see you've got very soft water here, and you can see much of the Midwest has very hard water. So the aquifers in the Midwest tend to be limestone, dolomitic type materials, so we tend to have much harder water. The total hardness is technically the sum of all polyvalent cations. So calcium, magnesium would include either Fe2+ or Fe3+, depending on its oxidation state, Mn2+ or Mn4+, again, depending on its oxidation state. So any polyvalent cation is a positively charged ion. In all practicality, it is the amount of calcium and magnesium ions. Those are the predominant minerals. And we divide it into carbonate hardness and non-carbonate hardness. So carbonate hardness is often called temporary hardness, and that's because if you heat the water, it will precipitate. So for instance, if you have a tea kettle that you've been using for a long period of time and you look on the inside of the tea kettle, you'll see a white precipitate. That is calcium, most likely calcium carbonate, that has dissolved or has precipitated. So it forms these insoluble carbonates. If it forms in a water heater, it actually decreases the heat transfer efficiency of the water heater. Now, if we're going to compare this to the alkalinity. Okay, so if we have, and it's easier to explain, so let's say we have a total hardness of 200 milligrams per liter and an alkalinity of 180 milligrams per liter. Your carbonate hardness can't be greater than the alkalinity because what we're assuming is that calcium and magnesium is associated with bicarbonate and carbonate, which make up the alkalinity. Those are the predominant ions that contribute to alkalinity in a fresh water. So in this case, the carbonate hardness would be equal to what? It's 180 milligrams per liter. Okay, it's equal to the alkalinity. So it's that portion of the hardness that's associated with your bicarbonate minerals. Okay, your bicarbonate and your carbonate, they're not really minerals, but your bicarbonate and your carbonate. If my total hardness was 160 milligrams per liter and my alkalinity was 180 milligrams per liter, my carbonate hardness is equal to what? $160. And these should, they're all. And this is a plot showing you the solubility of, and this is the solubility of calcium bicarbonate as a function of temperature. The major thing that I want you to take away from this is that as we increase temperature, we decrease the solubility. So this here is my temporary hardness. It's actually the temporary hardness due to calcium. So let me ask you this. When you do your lab test and you measure the hardness of cold water and hot water, try and get the water as hot as you can, as you can. Don't scald yourself. What would you expect? Do you expect them to be the same? Do you expect them to be different? And if they're different, how? So if I have you're going to measure the hardness of cold water and you're going to measure the hardness of the tap water. Do you expect them to be the same, or one to be greater or less than the other, and which way? So look here, this is my solubility. If I have really cold water, it's going to be about 5 degrees C. If I have hot water, it's going to be somewhere around 40. Okay. So the higher hardness, because the solubility decreases, you should see lower hardness in the hot water than you do in the cold water, assuming that your hardness is predominantly temporary hardness. Okay. So if you have, for instance, a high alkalinity, a high hardness and a high alkalinity, then most of your hardness is due to carbonate hardness and its temporary hardness. If, on the other hand, you had a high hardness and a low alkalinity, then most of your hardness is, or much more of your hardness is due to what we call permanent hardness. Okay. And the reason here is, if you look now, if we're looking at magnesium chloride, so we're looking at magnesium associated with chloride. This would be non-carbonate hardness because it's not associated with carbonate or bicarbonate. And here, notice as I increase temperature, I increase solubility. So Kayla, you're right there. If most of your hardness is non-carbonate hardness, then you will see an increase in hardness in the hot water compared to the cold water. And the same is true for calcium. So as I increase temperature, I increase the solubility. So for carbonate hardness, as I increase temperature, I decrease solubility. But for non-carbonate hardness, the opposite is true. This is magnesium sulfate. Again, here, you see as I increase temperature, and you're going to be operating pretty much in this range here. So as I increase temperature, I see an increase in solubility. For calcium sulfate, it's more complicated. What you are most likely dealing with are these species here, probably the water salt form here complex, and there's really not a whole lot of changes. So if you had a high sulfate, you may not see that much of a change with temperature. So one of the things that I want you to do is, when you're looking at your results, you have this data and you can look at it and try and ascertain, based on your hardness, based on your alkalinity, are your results consistent with the information that you have here? So non-carbonate hardness is that portion of calcium and magnesium associated with chloride. Nitrate and sulfate are your predominant ions. So let's go to the example where we had a carbonate hardness equal to 160, total hardness equal to 160 milligrams per liter as calcium carbonate, and I have an alkalinity of 180 milligrams per liter as calcium carbonate. My carbonate hardness is equal to what? 160 milligrams per liter, and my non-carbonate hardness is equal to, okay, if on the other hand, I have an alkalinity, we'll say it's the same thing, 180 milligrams per liter as calcium carbonate, but I have a total hardness of 220 milligrams per liter as calcium carbonate. My carbonate hardness is equal to 180, and my non-carbonate hardness is equal to 220 minus 180, or 40 milligrams per liter as calcium carbonate. Does that make sense? So these are the units that you can use for hardness. Milligrams per liter is calcium carbonate, which is what I've been using. In a water supply, in a fresh water, you can approximate, so if we have a fresh water, which is what we will be dealing with, milligrams per liter is essentially equal to parts per million. Grains per gallon of hardness are used in the ion exchange industry. And to convert from grains per gallon to milligrams per liter, you multiply grains per gallon by 17.1. And we can also use equivalents per liter or milli equivalents per liter. So let's do an example. And we'll just go through this. So we have a sample of water, contains a pH 7.2, and we're given the major ions. So for instance, this is exactly the information that you will have from the bottled water. And you're asked to calculate total hardness, carbonate hardness, non-carbonate hardness, alkalinity, and to construct a bar chart. So we can start this way. We have a list of all of our ions. Sure. Which, previous one or Alexa? Or this one?
This one is good, thank you.
Just let me know when, and I have everything posted. I should have posted it earlier, but I think I posted it yesterday. So you're going to go through exactly these calculations for your bottled water sample.
I'm all set, thank you.
Okay, good. Okay, so this is a table that's actually from Excel. So we have the major ions that you've been provided. Okay. And this is the concentration you're given. You're going to calculate the molecular weight or look up the atomic weight for each of the ions. And then you're going to calculate the number of equivalents. And for the most part, the number of equivalents that you're going to use is the charge. So where we have calcium, N is equal to 2. So this is 2 equivalents per mole. So it's equivalence, think of it as equivalence of charge. Magnesium is also 2. Sodium is 1. Potassium is 1. Bicarbonate is 1. Sulfate is 2. And chloride is 1. So then the next step you're going to do is you're going to calculate the equivalent weight. And your equivalent weight is just your equivalent weight, and I use milligrams per milli equivalent because we use that's your equivalence is in milli equivalents per liter. So I've got my molecular weight which is milligrams per millimole. Okay. And I divide that by N, which is milli equivalents per millimole. So all I've done is I've divided everything by 1,000. So instead of using grams per mole, I use milligrams per millimole. Instead of using equivalents per mole, I use milli equivalents per millimole. And it's one fewer conversion. So if I take this 40.1 milligrams per millimole, and I'm dividing that by 2 milli equivalents per millimole, I have 20.05 milligrams per milli equivalent. So that's the equivalent weight. And I have those calculated here. So I've calculated for each of the species. The next thing I'm going to do is I'm going to calculate the concentration in milli equivalents per liter. So I have 40 milligrams per liter. I divide that by 20 milligrams per milli equivalent. Milligrams cancel, and I have it's roughly 2 milli equivalents per liter. Here I have 10 milligrams per liter. I'm going to divide that by the equivalent weight, 12.15 milligrams per milli equivalent, and that's 0.823. Okay, so I'll do that for each. And then the last step, I'm going to take the milli equivalents per liter that I calculated. I'm going to multiply by 50 milli equivalents per milligrams per milli equivalent. This is the equivalent weight of calcium carbonate. Okay, and I've calculated it up here. So the molecular weight of calcium carbonate is 100 milligrams per millimole. Calcium carbonate, N is equal to 2. And we can think about that really when you do equivalents, you want to think about how many moles of either hydroxide or H plus can react. So carbonate can react with 2 moles of protons, produces carbonic acid. So because it reacts with 2, N is equal to 2. And that's where this 2 comes from. So the equivalent weight for calcium carbonate is 50. So if I multiply this 1.995 by 50, I get 99.8. Same thing here, I multiply this by 50, and I get 15.5. So this is how I'll calculate the concentrations in calcium, milligrams per liter as calcium carbonate. So you'll see for Iron Mountain, they give the calcium concentrations as the ion, so you'll have to go through this set of calculations. And we can check the ion balance. So what we would do is these are our cations, these are our anions, and if we sum these, then the sum is equal to 175.6 milligrams per liter as calcium carbonate. When you're adding these, you either add them in concentrations as milli equivalents per liter to check your ion balance, or milligrams per liter as calcium carbonate. You cannot use milligrams per liter. So do not use this. Okay? Do not use the concentration, straight concentration in milligrams per liter. You're going to use either milligrams per liter as calcium carbonate or milli equivalents per liter. And we calculate the sum here, and that is equal to 175.6, and it's actually perfect. Your ion balance should be plus or minus 10%. So rarely will you ever have it this exact. So the total hardness is the sum of the polyvalent cations. The only two polyvalent cations we have are calcium and magnesium. And we had 99.8 milligrams per liter as calcium carbonate and 41.2 milligrams per liter as calcium carbonate. So magnesium concentration. We add those, and the total hardness is 141 milligrams per liter. Now, the alkalinity is defined as it's the ability of a water to buffer the addition of an acid. And in most fresh waters, it is the concentration in milli equivalents per liter of bicarbonate plus carbonate plus OH minus minus H plus. You can use units of milli equivalents per liter or milligrams per liter as calcium carbonate. So you can use either units. Now, since the pH is 7.2, we can approximate alkalinity as equal to the bicarbonate concentration. So basically, if your pH is between about 6 to 8, you can make this approximation. So if we have 1.80 milli equivalents per liter, and we multiply by 50 milligrams per milli equivalent, equivalent weight of calcium carbonate, our alkalinity is 90.1 milligrams per liter as calcium carbonate. So our alkalinity is 90.1. Our total hardness we calculated as 141 milligrams per liter as calcium carbonate. So the carbonate hardness is equal to what? Yep, 90.1. And the non-carbonate hardness is the total hardness minus the carbonate hardness. So it's 50.9 milligrams per liter as calcium carbonate. And then we can, the last thing is to calculate a bar chart, and you will include your ions in order of predominance. So the order will be based on predominance. Calcium is present in the highest concentration, so we've got our cations first, then magnesium, then sodium, and then potassium. So you'll order them in predominance. We have bicarbonate, sulfate, and chloride. this here, I can now, the really nice thing about this is I can show my carbonate hardness. So let's just change here. So this portion here is my carbonate hardness. It's actually my carbonate hardness due to calcium. This portion here is my non-carbonate hardness due to calcium. And then this portion here is my non-carbonate hardness due to magnesium. So let me just change to use the pen. So this is my carbonate hardness due to calcium. Sorry to see that, but it's the carbonate hardness due to calcium. I tried to keep it the same color. This is my non-carbonate hardness due to calcium. And then what's green is my non-carbonate hardness due to magnesium. And that actually becomes really important. And you'll see, for those of you that are also in 483, you'll see this becomes really important in 483 when we look at lime soda ash softening, because depending on the type of hardness, that affects how we remove the ions, what chemicals we use, how much sludge is produced, how much it costs, etc. So here was our carbonate hardness. This is our non-carbonate hardness. So the red and the green contribute to the non-carbonate hardness. The yellow is our carbonate hardness, and this is our total hardness here. So it's a nice pictorial way of showing the different types of hardness. So I'll stop there. Happy to answer any questions. So any questions? How do you draw the bar chart? Okay, so let's go back to the bar chart. So basically, the way that I've drawn this is just on a piece of graph paper. So let's see, what was our calcium concentration? So the calcium concentration was about 100. So basically, if we look here, I want this scale so that this is 100 here. And then my magnesium concentration is a 41. So basically, this here would be 140. So that you see this is at 141. And then I've added, so then this would be about 160 or so. So basically, I've scaled it this way so that this distance here represents the calcium concentration. My bicarbonate concentration, remember, was 90. So this should be about 90 here. And then this would be 100, 10, 20, 30, 40. So this would be about 140 here. So if I add those, that should be about 145. Does that make sense?
Yeah, that makes sense. Is this order of the ions always going to be like that order?
It's always in the predominance. So whatever your predominant species is, it's typically going to be calcium. So typically it's going to be calcium, magnesium, sodium, and then bicarbonate. You could have, so for instance, in the Flint water that was treated, it was actually in this predominance, I believe, as I recall, in the raw water. But in the treated water, it was bicarbonate, chloride, and then sulfate. So the sulfate actually, so in the Flint water, I have this, and it was bicarbonate predominated, but then chloride was the next predominant ion, and then sulfate. So there you'd write, it's in order of predominance.
Okay, and then is the carbonate hardness and the total hardness always going to be like calcium and magnesium?
Almost always, yes.
Almost always, okay.
Rarely will you will never see, it would have to be a very, very unusual water. You will never see a natural water that the hardness isn't predominantly calcium and magnesium.
Okay.
Maybe in Mars.
Okay, thank you.
Not on Earth. You could, I suppose, in a industrial water have a hardness that where some other ions were the predominant ion, but in a natural water, calcium and magnesium will always be the predominant ions.
Okay.
Other questions? This makes sense? Hi, Joseph. Looks like you and I are the only ones left on.
Here you all up.
All right.